Hi again. So in this video we're going to see how we get that chi-square statistic, and I'll do the simulation again. I'm sorry I didn't realize until after recording that my the value at the bottom was underneath the recording window, so I'll come back to that and show you that again. Okay, so just like, well, I'm going to go down to the bottom just for a second here. Just like with the goodness of fit, our chi-squared is the same calculation, the observed minus expected squared over expected, and then we sum that up for each category. In this case we have 6, we have all the internal cells. But the way we get our expected is just a little bit different, okay? Because it's not something that we're given explicitly. It is given, but let me show you how it's given. So here's our formula here. Expected is going to be the row total times the column total over the grand total. And I'll show you why that works in a moment. But so let's kind of let's get a feel for this. So you'll notice I've got the same table here with only the totals, right? All the interior ones are blank, but the totals are the same, okay? So I've got the column, total column, and the total row. And then you see the 4, 2, 2, 3 is the grand total. Okay, so the interior numbers in the table, those are the observed, right? That's from the data, from the survey. But what we want to know is from this grand total and the total in approve and disapprove and of each job, what would we expect if under the null, right? Remember, so we're thinking null is independent, so we're setting everything up based on the null. If there is no association, what would we expect these interior numbers to be, okay? So what we do is row total. So for approve, our row total is 2,119 times the column total. So we're always going the row and column of the cell we're in, divided by the grand total, okay? So for this one, it's going to be 2,119, and I'll just use parentheses to indicate my multiplication here, times 1458 over 4223, okay? I'm going to do a couple of these and then I'll explain a little bit more, but see if you can understand why we're doing this. 2,119 times 1453 divided by 4223. And that is, with order of operations, goes left to right with multiplication. Oh, sorry, there's glare there. Left to right with the multiplication, so it is just fine. I don't need parentheses in the calculator. Now, notice we get a decimal, and that's okay. We're going to keep the decimals. I'm just noticing I got a different number than when I did this before. So do I have a typo? I do have a typo. 2,119 times 1458 divided by 4223. There we go. That looks better. Okay, so 731 point, and I'll just go 2 digits, 731.59. I'll put approximately because we are rounding that off, okay? So then next one over, you could go down as well. I'm just going to go across. Same row total, 2,119, and now our column total is 1,382 over 4223, okay? $13,4223. Okay, so I've got, this time I'm getting 693.45. Okay, I do third one, 2,119 over 1,383. Those two were very close in total. These two Democrats and Republicans in Congress, over 4223. Let's see what that comes up to be. Times 1,383 divided by 4223. Okay, 693 0.96 rounded. Okay. So have you figured out what's going on here? Think of this 2119 out of 4223. That is the overall approval rate, right? So that's the overall approval rate. Now, if this is roughly the same in each job, right, independent, we would expect those to be about the same, okay? Not exactly, because it's empirical data, it's not theoretical, but approximately the same, right? So that's essentially what we're doing, is we're taking, actually it's this way, we're taking this ratio, the 2119 over 4223, we're taking that ratio and multiplying it by the total under Obama and the total in each group, okay? So that's kind of what we're doing and how it relates to our previous independence test in 243. Okay, now I'm going to do the next row. You can feel free to pause it and do it yourself or skip ahead. This time we're going to do the same thing but with the 2104. And now I'm going to go down 1458 over our same grand total. So now we're only changing this number each time. This will be the general disapproval rate, right? Probability of disapprove would be this, and then we're multiplying that by the total in each job. Okay, so if these are close to what we observed, then we would say they're independent. Okay, so 2104 times 1458 over 4223. Something not right there. I did a multiply instead of divide. 2104 times 14. Oh my goodness. Must be Monday. Divided by 4223. I will double check with what I got last time. Yes, 726 times 0.41. Okay. Keep going with the 2104. This time we have 1382 for 4223. Okay, 688.55. And last one is 2104 times 1383 for 4223. Did it again. 2104 times 1383 divided by, I keep forgetting to hit that divide by, 4223. You're missing, just missing that key. Okay, so 689.04. Okay, so these are our expected under the null, assuming that there is no association, right? Which would mean that these rates are the same for each job, okay? Or you could also look at it the other way using the other ratio. Okay, so now remember our chi-squared is kind of this difference. We're taking the difference between the observed and expected, but some will be negative, some will be positive, so we're squaring it. Okay, and then we're also making it relative to the size of the group. So we're dividing it by the expected, and then we're adding that up for each term, okay? So we will have 6 of these, so you can see it does get a little tedious. We are going to use technology. It does get a little tedious after a while. Okay, so I need to get my original table back to get my observed, right? So in the data, 842 approved of the job President Obama was doing out of this survey. So that's 842 minus, under independence with these totals, we would expect 731.59. Okay, I'm going to square that and divide by expected again, 731.59. Okay, I'm going to go across and approve those who approved of Democrats in Congress is 736 minus the expected that we got was 693.45 squared over that again, 693.45. Okay. Now, I'm generally going to require you to write out one of these terms, and you can do a dot, dot, dot. I'm going to do the last one, so I'm going to say dot, dot, dot for those middle three. I'm going to do the last one. That's sometimes how we show a pattern. In math, I will do the last one, which is 842 minus 689.04 squared over 689.04. Okay. Now, these are going to magically add up to, you can do a equals or approximately equal, our chi-squared statistic. Okay. And in our simulation, even before we do the simulation, once we put in the data, it actually calculates this all for us. That's where we got the 106,351. So I'm going to write that down. Okay. And if you click on Show Details, this is a really nice little table here. I can make it a little bigger. It shows you the original in the kind of just the regular gray or black type is the observed, same as the data. And then here's the key down here. So the expected is in green. So we could double check all of our expected real quick. They just do one digit. I did 2, so that's fine. And then the blue is if we did each term individually. That's the contribution. So if I did this term here, that's the contribution of that cell to the chi-squared, and then we're adding them together. So each cell has a contribution to the chi-square variable, test statistic. And so then if we added up all these blue numbers, that's the contribution to chi-squared. That total is 106,351. Okay? 106.351 to be more specific. Now, if you want to go ahead and check that out, do this whole calculation, that is totally fine. I would recommend the Desmos online calculator because you can see everything and you can proofread versus a smaller window calculator where it'd be really hard to, if you miss a digit, it'd be really hard to find where that was, right? So I would recommend Desmos if you're doing that. But what I'm going to require, and you should check with your instructor if you have a different instructor, what I'm going to require is writing out the pattern showing that you know how this is developed, and then you can get this chi-squared test statistic from technology. Either StatKey or I'll show you on GeoGebra as well. Okay, so I'm just going to make a note here that there are 6 terms in this summation. I'm going to say write out the first one, and then use StatKey or GeoGebra. For the test statistic. Okay, I am more concerned about understanding the concept of why we're doing this, how this statistic is formed, and what the p-value means versus the, rote calculation. Okay, that can be very tedious. So once you feel like you understand this process and what's going on, please use technology. Okay. Okay, well, let's keep going with our test then, and we'll come back to that simulation. Another thing we need to know are the degrees of freedom, the degrees of freedom. So because we have rows and columns this time, it is the number of rows minus 1 times the number of columns minus 1. So in this case, I'll write it underneath. We have 2 rows, 2 minus 1. Remember, the rows go across. The columns are like, columns on a building. They go down. And we have 3 columns. And remember, we're not counting the totals. Again, we're only counting the data. And we always subtract 1, because if we knew 2 of them, or if we knew everyone except 1, we could fill in the other one, right? So because we have our total at the bottom, if we knew the first one, we could fill in this number by subtracting. So degrees of freedom kind of gets at that idea. If we have these 3 columns, if we knew 2 of them and the total, we could subtract to get that last one. So everything varies except the last. Everything can vary except the last thing. Okay, so let me go back down here. Okay, so 2 minus 1 is 1, and 3 minus 1 is 2. So 1 times 2 equals 2. So we have 2 degrees of freedom. Okay? So let's go ahead and find our p-value and write the conclusion for this test. Okay, so p-value, remember, this is the chance of the observed result or toward the tail, assuming the null is true, right? So assuming that we have these expected counts, the difference, the chi-squared, we want to know what's the chance that the chi-squared is greater than 106.351, okay? Okay, let's go back to the simulation. So I'm going to go ahead and reset my plot. I've got the original data here, generate the 2,000 samples, and that changes the scale back. You can see the highest one had a chi-squared statistic of just under 16, okay, and we're going up to 106. So it is a right tail test because it's bumping up against 0. 0 is very little difference in the expected and observed, right? So very little difference, going out to more and more difference on the right as we go to the right. So when I click on right tail, I'm going to enter my 106.351, and we get a p-value of 0, okay? And not just 0, but way, 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 way. We can see it's way further. So there is a lot of difference between the observed and the expected, right? So our p-value is 0. And let's write our conclusion. With a p-value of 0, let me move this up a little bit. Okay, remember, small is significant. We reject the null hypothesis. There is evidence for the claim. And I could have said strong evidence or very strong evidence as well because it's so small. There is evidence of an association between the approval ratings. I want to put my context in here. And the jobs of President Obama, Democrats in Congress, and Republicans in Congress. Okay, so there was a significant difference between the observed and expected across all of the categories, right? So we say there is evidence. We could say dependence. Dependence, the word dependence tends to convey causation. So things can be associated and one not causing the other. So that's why I'm going to tend to use the word association or relationship versus dependent. Sometimes you will see that, though, kind of depends on the textbook. But just to be aware, we don't want to convey causation. We just want to state if there's a relationship or not, or independent or not. Okay? Okay, great. Well, let's stop here and we will go to the next page. I'll show you that in the next video.